Good morning to all of you.
Good morning, sir.
Morning, sir.
Good morning. Good morning. So, is my screen visible?
Yes, it is
Yes,
visible.
sir.
So, are there any questions, doubts, anybody? Anybody wants to ask any questions, doubts? Okay, so if there are no questions and doubts, then let me start. So, so the last class I was talking about how to develop the element level governing equations.
So,
Yes.
can you please tell me about inter-element compatibility? I did not get started. So, like,
Okay. So I was talking about basically the element level governing equations. So since there is a question, so let me repeat what I did. So I had talked about when we assume the approximate solution within an element, approximate solution within an element. So we said there are three things. The differentiability requirement which is within the element, differentiability, and then the completeness, and third was inter-element compatibility. So yeah, there is so I had explained that whatever approximate solution you assume it should be differentiable up to the highest order derivative present in the big form or integral functional. And then the completeness means whatever highest degree term is present in the approximate solution, so all the starting from constant, all the lower degree terms should be present in the approximate solution, so that is completeness. And the inter element compatibility is that primary variables should be continuous. So the last one, if you look at what I had stated, is that primary variables primary variables should be continuous across the elements. So as an example, I said that, see, to enforce the continuity, that means what it means is that if I have let's say the differential equation is a second order differential equation, that is the truss element. So for the truss element, the governing differential equation was d by dx of E a du by dx plus q equal to 0. So in that the primary variable is actually u. So u should be continuous when we have the assembly of elements, and that continuity can be enforced if at the in nodes where the other elements are going to get connected, we have primary variables as degree of freedom. So I had said for this that, say, the u at node 1, so if this is node 1 and this is node 2, these should be there. U is a primary variable, so the value of u at node 1 should be there as a degree of freedom. Value of primary variable at node 2, that is u2, should be there as a degree of freedom. So if this is there, then we can, during the assembly of the elements, we can ensure that there is a continuity of primary variable, that is u in this case. So what that means is, say for example, no, if you have an assembly of no elements, when you do the assembly, let us say this is the three element discretization. So the global node numbers are 1, 2, 3, and 4, and the elements are, this is element 1, this is element 2, this is element 3. So now at the common nodes, at this node, we should have, when we calculate the value of u, either from the first node at this point, or from the second node, no, at the same node from the second element. So at this node number 2, which is common to element 1 and 2, if we calculate u from element 1, and if we calculate the value of u at node 2 from element 2, it should be same. So that can be ensured now when the, so now if we have in element 1 and 2, in both the this node has got the degree of freedom as the primary variable, so we can say that at this node the value of u is same for both the node 2 belonging to element 1 and node 2 belonging to element 2. So that is how we ensure the continuity of primary variables across the element, and that is known as the inter-element compatibility, or simply sometimes we call it as compatibility. So similarly, we'll have the condition at node 3 and so on. So depending on the situation. So then another example, I had taken the fourth order differential equation, that is differential equation based on Euler-Bernoulli beam theory. So there the element level, the differential equation was d2 by dx square operating onto ei d2v by dx square minus q equal to 0. So in that, when we have seen the primary variables are v and dv by dx for Euler-Bernoulli beam. So now primary variables should be continuous across the element, and for that we need the primary variables has degrees of freedom at the end nodes. So when we have assembly of these elements, we can ensure that primary variables, in this case v and dv by dx, are continuous. So we should have Euler-Bernoulli beam element, which is governed by fourth order differential equation. We should have the value of deflection and value of slope, that is dv by dx at node 1 and v2, and dv by dx at node 2. So these should be continuous. So that is what I had talked about, this inter-element compatibility. So is this clear?
Thank you, sir.
Yeah. So yeah, so the last class I talked about how to develop the element level governing equations from the big form directly. Now let me also demonstrate you that you can develop the element level governing equation from the integral function. So for the same problem, I will demonstrate that, and maybe some of you might have done this, but I just want for the benefit of all the participants, I want to again discuss that. So next is element level governing equation from integral functional. So no, you remember already that for let me take that this truss problem, the truss element problem. So we have already said the local coordinate is capital X. This is node 1, this is node 2, and we have the value of primary variables as degree of freedom at the end node, so u1 and u2. So and the length of the element is small l. That is the element length, and the Young's modulus is E, and the cross sectional area is A. And so these are the properties. And in terms of forces, if you look at in the element, so we have distributed force Q, and we have the forces at the in nodes, these two nodes. So let us say this is Q1, this is the the force coming from the element on the left side of this element, and similarly we will have the force coming onto this element from the element on the right side of this. So those are the kind of internal forces, so that is Q2. So for this we have already derived the integral functional. Only thing is I am writing for element. So the integral functional I which we have derived is integration 0 to L EA, and then we had du by now dx. I am using the local coordinate x which is having origin at the left end of the element. So du by dx whole square dx minus integration 0 to L u into q dx, and then we have the potential of these forces q1 and q2. So that is q1 into u1 minus q2 into u2. So this we have already discussed, how to get from the differential equation for this problem, how to get the integral function, or directly also you can write this is nothing but strain energy, this is nothing but potential of distributed force q, this is the potential of force q1 at left end, and this is the potential of force q2 at the right end. So you can also write this directly, this integral function. Since we are going to substitute the approximation for u in terms of product of vectors and matrices and vectors, so we write this in the form in which the product is defined. So this is half integration 0 to L, and then this CA, and du by dx is a scalar quantity, which is actually the epsilon xx, the strain along x direction. So I can write the same thing as du by dx transpose into du by dx. This is same as what is written here, only because it is a scalar. So du by dx transpose into du by dx is nothing but no the same du by dx whole square dx, and minus integration 0 to L. Again, note on the left hand side I want to take the transpose quantity. So this u into q, again u is a scalar, I can write that as u transpose into q dx. And the last term, let me write it as product of two vectors. So we will have say u1 u2 transpose, and then we will have minus q1 and plus q2. So that you will give it will give you the same term what I have just written here. If you multiply this, you take u1 u2 transpose and multiply by minus q1 q2, and then take this minus, so you'll get the same term what we have got here. This term, this term. So now this is the integral functional, and the criteria for choosing the approximate solution is same. That no, because in the integral functional the highest order derivative of u is du by dx. So whatever approximate solution we assume, it should be differentiable once. So approximate solution similar to what we did in the last class. So we assume that u is equal to a0 plus a1x. Why a1x? Because the highest order derivative in the integral functional is first derivative. So we should have a linear term so that it is differentiable once, and then we add a naught so that it is complete. That means a1x is a linear term in x. So before that, constant term should be there as per the completeness requirement. And then we look at the inter-element compatibility. So primary variables that in this case u and u should be there as a degree of freedom at in node. So there are two variables u1 and u2 as elemental degrees of freedom. So we should have corresponding two constants in the approximate solution. So a0 and a1. So they are already there. So that means we will be able to ensure the inter-element compatibility based on this approximate solution. And then as done in the last class, we express a0 a1 in terms of u1 u2, and then write this in terms of the interpolation functions or shape functions. So we have already seen that this is n1 n2 into u1 u2. We can write it like this. So now where now we also write this as h into de. We have already defined n1 n2, and this is de. So h is known as the interpolation matrix, interpolation matrix, and DE is known as vector of elemental degrees of freedom. Vector of elemental degrees of freedom. So this is one thing, U equal to H into D. H is N1 N2 into U1 U2. N1 is 1 minus X by L, and no, your N2 is X by L. So that also you have seen. N1 is last class we did 1 minus X by L, and N2 is X by L. And then we need this du by dx in the integral functional or in the big form as we did earlier. So du by dx, we differentiate basically this with respect to x. So here n1 and n2 are the only functions of x, so we differentiate these terms. So we will get this as dn1 by dx, dn2 by dx into u1 u2. So we are just differentiating basically, this equation. So then what we do, we have another set of notations. So we refer this as B into DE. So this is B and this is D. D we have already said vector of elemental degrees of freedom, and B is known as strain displacement matrix. In the solid mechanics problems, we call it as strain displacement. If it is a thermal conduction problem, then it would be temperature gradient matrix. No, and in the case of solid mechanics problems, it is strain displacement matrix. Strain displacement matrix. Now, so after this approximation for u, we substitute this in the integral functional. So now, if you look at I can be written as half integration 0 to L, and then we have this EA and du by dx transpose. Now, if you look at in the integral functional, so we have here du by dx transpose, that is this term, and du by dx is B into DE. So du by dx transpose would become D transpose into B transpose. So we write this as D transpose into B transpose, and then again we have du by dx. So that is B into DE, and then dx minus integration 0 to L U transpose. So U is H into D, that is written here. So U transpose would be D transpose into H transpose. So we will have D transpose into H transpose into Q dx. And then of course we have this other term due to the forces at the ends. We have this U1 U2 transpose into minus Q1 Q2. So that I can write it as minus D transpose into minus Q1 Q2. So this is your integral functional. After substituting the approximation of u and u by dx, we can write like this. Now in this, always see, as far as the, for example, this A and B are concerned, they could be functions of capital X. So we want to keep those inside the integral functional. But as far as D is concerned, D is the U1 and U2, which are the values of U at node 1 and 2. So they are independent of capital X. So these two terms can be taken out of the integration sign. So I can write this as half, and then D trans, because no, I can take this on the left side. So I am taking D transpose, and then integration 0 to L, and then you have this EA, and then B transpose into B and dx. So this, and then into DE. So this I have done, this D I have taken on the right hand side. And similarly, now in this term, I can take D transpose out of the integration sign. So I can write that as D transpose into integration 0 to L H transpose into Q dx. And of course, the last term is D transpose into minus Q1 Q2. So yeah, now we call this term as actually the stiffness element level stiffness matrix. So we further write I as half of D transpose into KE. So this term is referred to as KE and then into DE minus DE transpose E superscript E stands for element. No, that these are for element. They are at the element level, and this is, let us refer to this as no load vector due to distributed externally applied distributed force Q. So this is your F external, and then we have minus D transpose, and let us refer to that as F internal for the element. So F internal is this. So you can say that here. So now in this, where KE is nothing but integration 0 to L EA into B transpose into B dx. Hello, am I audible? Hello, are you following?
Yes, yes,
Yes,
sir.
sir, audible, sir.
You're
Okay.
Yes,
audible.
sir.
Yes, sir.
So yeah, so we get this as the no KE, the element level stiffness matrix as EA into B transpose into B dx. And we call it as, so the name for this is, we call it as element level stiffness matrix. Element level stiffness matrix. And then your F external is F external for the element is integration 0 to L H transpose into Q dx, and we call this as element level external load vector. So either you can say element label or elemental, that is also you can write. So you can say, let me use elemental. You can, for a element level, I know all places you can either write element level or you can say elemental. So elemental external load vector. And then we have this F internal for the element. So this is minus Q1, Q2, and this we call as elemental internal load vector. Why elemental? Because when we have assembly of element, then these forces become internal to the system. So that is why no, I'm using the term no, external, sorry, internal, because in the assembly of elements it is going to be internal. Of course, for one element this is also external, but I'm using the term elemental internal load vector. Yeah, so now once you have this, so then we want to, from this we want to develop the element level governing equation. So we know that the satisfaction of the original differential equation is equivalent to saying that delta I equal to 0. So I can say that for equilibrium, our satisfaction of the original differential equation is equivalent to saying that delta of I, the first variation of the integral functional I, the total potential energy functional I should be equal to 0. So from this you can say that if you write the expression for delta I, so I know you see this I is half of D transpose into K into D. When we take the variation, variation is taken with respect to unknown quantities. And unknown quantities here are unknown quantities actually vector D, the vector of unknown elemental degrees of freedom. That is u1 and u2. Those are the two unknowns. If we know u1 and u2, then we know the displacement approximation within the element. We know the differentiation of that will give you the strain, and from there we will get the stress and so on. So variational operator is going with the unknown quantities. So the unknown quantity here is the vector d. So when we write delta is for the first term, the variation of first term, so half of uh, delta D transpose. So I'm using this delta with this D. and then the other term we keep as it is ke into de, and then plus the variation of the second term, so that is d on the right hand side. So we will have then half d transpose into ke and then delta of de. So now I'm treating first d as the first function and second d as the second function. So it is first function into second plus first function into variation of second. So that is how you get these two terms in the variation delta I. And then minus we will have delta of d transpose into f external for the element minus delta of d transpose into f internal for the element, and this is actually equal to 0. So then you can say that delta I, now if you look at the these terms, no, if you look at for the problem at hand, you will see that k is going to be of size 2 by 2, d is of size 1 by 2. In that you have no sorry 2 by 1, not 1 by 2. D is 2 by 1, and then D transpose would become 1 by 2. So finally when you multiply all three, you will get a scalar quantity. So similarly this is also a scalar as a whole. So what I can do is I can replace this quantity by its transpose. So I can put a transpose. So when I write the transpose, so you will have the transpose of that would be half of delta dE transpose into ke into d, and when you write the transpose of second, so half will be there. So if you have the product of three matrices ABC whole transpose, so that would be C transpose B transpose into A transpose. So this will come first, so it would become delta of D transpose, then KE transpose, since K is symmetric, so KE transpose is equal to KE, and then we will have D transpose, so transpose will become DE. So that is how the second term can be written like that, and the other terms of course are written as it is delta of D transpose into F external for the element minus delta of D transpose into F internal for the element, and this is equal to 0.
Sir, how there will be whole transfer on second term?
Hold, yeah, so because it is a scalar, finally you see the whole multiplication is giving you 1 by 1, so that means it is a scalar. So scalar can always be written as its transpose. It is one and the same thing. So what it means is that when I calculate this whole product, this and I will get an expression, and if I take its transpose, it is going to be the same thing. It will give you the same quantity, same expression. So for a scalar can always be replaced by its transpose. So that is how I am saying that I can replace the second term by its transpose. The first term also can be replaced by its transpose, but why I am doing second term, so that I have delta D transpose on the left hand side, and so that in all the terms I have delta D transpose on the left hand side. So that is how I am doing this. So any scalar can always be written as its transpose. So it is one and the same thing. Okay.
Okay, sir. Okay, sir. Thank you. And sir, why the variation is only applicable for that D term?
Yeah, as I said, the variation here is variation is with of unknown quantity. Unknowns are in the in this whole expression. See, the unknown is only u1 and u2, and that is nothing but your vector de. So that is why the variation is with respect no is taken with de, because d is the only unknown vector. So we are only varying we are taking the variation or giving the virtual change only in the unknown displacements u1 and u2. So that is why the variation with only de. Other k is known, f external is known, f internal is also assumed to be a known quantity. So the variation is with respect to only DE. Okay.
Okay, sir. Thank you.
Yeah. So now see what you can do. If you look at this expression, I can write no, this delta I is equal to, now if you see these two terms are same, so I can combine them. So I can write this as delta of dE transpose, and let me take delta D transpose common in all the terms. So then I can write in the inside I can write this we will have KE into D, delta D transpose. Now these two terms are combined, half of becomes total 1. So we will have delta D transpose K into D, delta D transpose is taken as common. So from the second term we will have minus F external for the element because delta D is already taken common, minus F internal for the element, and then this whole thing is actually equal to 0. Now the variation in D is arbitrary. So since delta DE is arbitrary, so no, but it's still no this product. So now if you look at this delta I, it is product of two things, delta D transpose, and the other side no, we have all these terms. So since delta D is arbitrary, that means for any arbitrary values of delta D, this product should be equal to 0. So that will be possible only if the second term is actually equal to a null vector. So I know from since delta D is arbitrary, we get this we need to have this KE into DE minus F external for the element minus F internal for the element must be equal to a null vector. So if this
Sir,
is a null vector, then irrespective of what values of delta D we take, this product will
hello.
always be, yeah,
For this
yes,
D
please.
have to verify, for this
Uh,
DE have to verify the boundary condition for how this D can be a arbitrary.
No, this is we are talking about the element, no? So the boundary condition will come only at the in the elements, no, in nodes, no, and in the elements. Right now we are talking about a element anywhere within the structure. So when the element is there anywhere within the structure, there no U1, U1 in U2 both of them are unknown. So the delta D will be arbitrary. Of course, the nodes ultimately in the assembly at the nodes where U is prescribed as a boundary condition, there no then that particular variation in that degree of freedom will be 0. But otherwise, it is arbitrary. No, if you have the element anywhere. Okay.
Okay, sir.
Yeah, we are talking about the element anywhere inside the structure. So in general, no, when it is inside the structure, there would be no boundary condition. So both U1 and U2 would be unknown. So based on that, we are saying that delta D is arbitrary. So therefore, for this product to be 0, we require the second term to be a null vector. So then, irrespective of what values we choose for delta U1 and delta U2, since the second term is a null vector, this will always be 0. So the condition delta equal to 0 will be satisfied. So now we get you can take the force terms on the right hand side. So you can say that this is Ke into De is equal to F external for the element plus F internal for the element, and this we call as element level governing equation. And if you see, this is same as what we did from the weak form also. The form, if you look at it, is the same. Whatever way the weak form we had written, so this is actually similar to that. So whatever we have now, this whole equation is element level governing equation or elemental governing equation. Now, so now let me get the expressions for Ke F external. For a case where let us say that A within the element is constant. So let us say for constant A and Q. over an element or within an element. So for that we will have, now if you look at the element level stiffness matrix Ke, so Ke, since Ea is constant within the element, although it can be function of capital X, so if it is constant we can take that out of the integration sign, so it would be Ea integration 0 to L, and then we have B transpose into B dx. And we have already said that B is nothing but dn1 by dx, dn2 by dx. If we take its transpose, it will become a column vector. So dn1 by dx, dn2 by dx into B, which is dn1 by dx, dn2 by dx, and into dx. So yeah, now you can write this as, if you multiply these two the vectors, so it will become a 2 by 2 matrix. So we will have dn1 by dx whole square, and then dn1 by dx into dn2 by dx, and then we will have dn2 by dx into dn1 by dx, and dn2 by dx whole square into dx. So we already know that n1 is 1 minus x by L. So dn1 by dx will become minus 1 upon L, and dn2 by dx is x by L. So its derivative with respect to x will become 1 by L. So you can say that no, finally this Ke would be equal to Ea integration 0 to L, dn1 by dx square will become 1 by L square, and dn1 by dx into dn2 by dx will become 1 minus L square, 1 minus L square, and 1 by L square dx. And now you integrate each term. So because it is constant, so the integration is going to be L. So when you multiply, you can take 1 by L common from all of these. So you can write this as 1 minus 1 minus 1 and 1. So if Ea is constant within the element, then the element level stiffness matrix is Ea by L 1 minus 1 minus 1 1. So this you get as the element level stiffness matrix. Similarly, if you look at the external load vector F external E, since Q is constant within the element, so we can take that out of the integration sign. So we will have integration 0 to L H transpose into Q dx. And we know that this H transpose is n1 n2 into Q is already taken out of the integration sign, so this will not be there. So dx, and if you integrate n1, which is 1 minus x by L, if you integrate it, that would be L by 2. So this will become you can take QL by 2 as common, so it will be 1 and 1. So this is going to be the element level external load vector for constant Q within an element. So yeah, this is how you get the element level governing equation. We have defined already what is Ke and what is F external for this. Now so you I know some of these might be basically a repetition for some of you, because you might have already done, but because no, for every problem I am not going to do all of these, because it will not be doable manually. You can only do some for many elements what we are going to discuss subsequently, you can do only through the computer programs. So that is why I am demonstrating again for the simple problem, that how you get these quantities. And let me also discuss how we use this to solve problems. So now let us say that we have a rod, and this rod is subjected to the load along the length direction. So this is Q, and we want to solve. So let us say this end is fixed, and this is a distributed force Q, and Q is constant, let us say, throughout the rod, and its Young's modulus of the rod is E, and the cross sectional area is A. And let us say the total length of the rod is 2L. and we want to solve this using finite element. So we want to find out the displacement, strain, stress, everything in this rod using finite element. So using this two noded truss element which we have discussed just now. So now what you can actually do is the minimum is, of course, you can discretize this using one element, but let me show you the solution procedure by discretizing this into two elements. Although you can discretize it into any number of elements. So let us discretize this whole thing into two elements. So two element means an equal length elements. So the global node numbers will be, this is global node number 1, this is global node number 2, this is global node number 3. This is element 1, this is element 2. And the length of each element is going to be L and L. So this is the discretization. So now once we have already developed the element level governing equation, we have also derived the expressions for the stiffness matrix, load vector. So the next step is actually assembly. We have to assemble these finite elements, and this is during the assembly process when we enforce the inter-element compatibility requirement. So now we will say that at node 1, of course, you have the displacement as u1, and at node 2 you have displacement u2. So which is same for the second element of second node of element 1 and first node of element 2. The u is same. So that is how the continuity of u is enforced. And of course, node number 3 you have the displacement u3. So now if you look at before imposing the boundary conditions, you will have three displacement unknowns, u1, u2 and u3. So the overall size of the my stiffness matrix will be 3 by 3. This into the displacement vector. So the displacement, as I already said, there are three nodes. First node the displacement is u1, second node the displacement is u2, and third node the displacement is u3. And then you will have load vectors. So you will have external load vector, and plus you will have the internal load vector. So we will have plus here the internal load vector. So this is what you are going to have. Now how do we assemble? So now if you look at the element number 1, it is consisting of global node number 1 and 2. So that means the the element level governing equation of the first element will go to the degrees of freedom corresponding to u1 and u2. So that means first two rows and columns. So when you take the first element, if you take its stiffness matrix, so the first row and first column of stiffness matrix of first element will go to the first row and first column of the global stiffness matrix, that is the assembled stiffness matrix. So for writing that, since EA by L, each element is of length L, small l, and the EA is same for both the elements. So I can take this EA by L as common. So then the first row and first column of first element stiffness matrix goes to first no row and first column of the global stiffness matrix. Then first row, second column. So if you look at for the element 1, the stiffness matrix is 1. The stiffness matrix is this EA by L, 1 minus 1 minus 1 and 1. So this is the first row and first column, it goes here. And then the first row, second column, that is minus 1, will go to the first row and second column. Why? Because the element 1 is consisting of global node numbers 1 and 2. So the minus 1 will go here. Then this is the second row, first column, will go to the global second row and first column. So it is minus 1 here. Then this one, second row, second column, will go to the global second row and second column. So it will be added here. Now when you talk of the second element is consisting of global node numbers 2 and 3. That is, for the second element, the first local node is actually global node 2, and the second local node for element 2 is global node 3. So that means first row and first row and first column of second element will go to second row and second column, and similarly the third row or column of the second row and column of the second element will go to the global third row and third column. So now when I take the second element, so again ke is same, because in this case the properties are same, so which is 1 minus 1 minus 1 and 1. So now for the second element, this term, that is first row and first column of second element, will go to the global second row and second column, because first node is global node number 2, and at global node number 2 we have degree of freedom as u2, so it will be added here, so this will be plus 1, and then this term, this minus 1, will go, that is a second element first row second column, will go to the second row and third column, so we will be adding over here. Then this term, no, the first second row first column, second row of the second element will go to the third row, and the first column will go to the second column, so we will be adding it over here, and then the second row second column of second element will be go to the global third row and third column, so it would be added here, and wherever we don't have anything we just put 0. So this is the assembled stiffness matrix. Okay. Then similarly, if you look at the F external, so for the first element it will go to the the first row and second row in the global system. So we will have here QL by 2, QL by 2. And for the second element, because it is corresponding to global degrees of freedom U2 and U3, so for the second element it will go to the second column, second row and third row. So these contributions are coming from the first element, and these contributions are coming from the second element. Now as far as the internal load is concerned, internal load vector, so we have to differentiate the internal load vector for the first element and second element. So the first element is, let us say, q11 with a minus sign, and q21 superscript is for the element number. So the internal load vector of the first element goes to the first and second rows of global system, and then the element internal load vector for the second element will go to the second and third rows of the global system. So we will have minus q12, that is internal load vector for the second element is q22. So this is how the assembly really is going to be there, the assembled system. So you would have learned, but I wanted to demonstrate that this is how you enforce the element level governing equations. So now if you look at this is the now the the system level equilibrium equation, system level equation for the system as a whole, the system consisting of two elements. Now next thing comes is the boundary conditions. So now depending on what boundary conditions we have, so boundary conditions, so now as I said, no, for this case we are having node 1 is actually fixed, so then you will have u1 will be actually equal to 0, that is one boundary condition. And if you look at the second is the last node, that is node number 3, that is free, so the internal load vector q22 is going to be actually 0 there, because no, this node there is no concentrated force applied at this node or at this node, so q22, which is the force at node 3, so that is 0 because there is no externally applied concentrated force at this node, so that is 0. Now so now u1 is already known to be 0, u2 u3 are unknown in this case, so u2 and u3 are unknown, q22 is actually 0. Now what about this q21 minus q12? So for that, the third thing is, for the third one, let me draw the free body diagram of known your basically the node 2. So if I cut the take a section just left of node 2 and take another section just right of node 2, so you will have the free body diagram of node 2 is going to be this side. Now see this q, if you look at q12 is the force on the element. So the force on the node is going to be in the opposite direction, so this would be q12, and this side similarly opposite of what we have in the element. So let me again show you that when we are talking of element 1, so now we are saying that this is q11 and this is q21. When you talk of element number 2, so this side is what we have q12 and this side we have q22. So this is a common node which we are talking about. So at the node 2, opposite of this I'm sorry, this is q21, not the q12. So this is q21, and opposite of this q12 is going to act this side, so this will be q12. And as of now there is no concentrated force at node number 2. So although let me take that as a p, but p actually equal to 0, that means there is no concentrated force. Now we write the equilibrium equation for this, so we get minus q21 plus q12 plus p equal to 0. So then you can write, this is the equilibrium equation. So you can actually write this as q21 minus q12 is equal to p. And for the given case, since p is 0, so q21 minus q12 is actually equal to 0. So this is the third boundary condition, that no further this q21 minus q12, q21 minus q12 is equal to p. So if there was a concentrated force at node 2, then we would have used that, put that value, but since that is 0, so this is equal to 0. So now if you look at this equation, now what are the unknowns? So u1 is already known, equal to 0, u2 and u3 are unknowns, and then now see this q11, this term is an unknown, q21 minus q12 is 0, q22 is 0, so the unknowns are 3, u2, u3 and q11, these are the 3 unknowns, and these are 3 equations. So we can solve for the 2 unknowns u2, u3 and the reaction unknown q11, that is force on element 1 at node 1, internal force.
Excuse me, sir.
Yeah.
So for the boundary condition 3, like the third boundary condition, you draw the FBD like Q12 and Q12. I think so. If we see the element 1 and 2, so for the element 1 at the second node, its direction is to in this direction, means towards the positive x-axis, and here
Yeah,
it is
so
towards the
this,
negative
so that is
x-axis.
what I said. No, this is the force acting on the this node. If you look at the node 1 and 2, this is the
Yes, sir.
force acting on the element. So
Yes,
when you
sir.
look at the node, when we take a cut section here, the force will be in the opposite direction. We are taking a cut section over here. So the force is going to be opposite direction. So this is what is correct free body diagram of the node. If you look at Q21 is the force on the element, uh, at this node 2. So then on the node, this force, when I draw the free body diagram of the node, it is in the opposite direction. Similarly, when you look at this, so this Q12 is the force on element 2 first node. When I draw the free body diagram of node 2, its opposite is going to act on the this node, this particular node 2, global node number 2. So that is how I have shown this. So what is shown is correct. These are the forces acting on the node, whereas these are the forces acting on the element, this and this. So that is how they are shown in the opposite directions.
Thank you, sir.
Yeah. So now once you have done this, I know you about the boundary condition. So then usually what we do, first we solve for the unknown displacement. So now if you look at the second and third equation, because u1 is equal to 0, so u1 will not come in the second and third equation. So we can take the second and third equation, solve for u2 and u3, and after solving for u2 and u3 from first equation we can solve for q11, and that's the final solution. So that is how you solve the entire problem. So what I'm saying is that first we solve for u2 and u3 from second and third equations, then solve for q11 from first equation. So this is how the solution procedure is. So if you look at the second and third equation, so you have EA by L, and then you have 2. If you look at the second and third equation, so second equation, when I took this EA by L minus 1 into U1, U1 is 0, so that those terms will not be there. So you will have only these terms, 2 minus 1 and 1 into U2 U3 is equal to, then you solve this side, right hand side, you will have here QL and here QL by 2, because second node QL by 2 plus QL by 2 is equal to QL, and we have already said that this uh, Q1 Q21 minus Q12 is equal to 0. So now you can solve. I am not going to solve this. You can solve these two equations for u2 and u3, and once you have solved for u2 and u3, then you can go to the first equation and solve for q11. So the first equation is already, now you have EA by L, and then you have this u1 minus u2. u1 is already 0. I am looking at the first equation. So you have EA by L, and then U1 minus U2 is equal to QL by 2 minus Q11 is equal to QL by 2 minus Q11. So now once you have solved for U2 and U3 from this equation, U1 is already 0, you put the value of U2, you can solve for Q11. And once you have solved for the U1, U2 and U3, and then you want U anywhere within the element, so for anywhere within the first element, for for the first element, you will have then U anywhere within the element is going to be n1 n2 into u1 u2. u1 u2 you would have, u1 is 0 and u2 you would have solved, so you can get U anywhere within the element. And then the strain epsilon xx is du by dx, which will be dn1 by dx dn2 by dx into u1 u2 are known to you, so you can calculate epsilon xx, and then the stress anywhere within the first element sigma xx you can calculate as E into epsilon xx. So similarly, when you take the second element you will have U as again the same shape functions n1 and n2, which are 1 minus x by L and x by L, but this will be u2 and u3, the global degrees of freedom 2 and 3. So u2 and u3 would have already solved, and then now you put the values of u2 and u3 and the value of capital X, and you can find out U anywhere within the second element using this expression. And then the epsilon xx would be du by dx, which would be dn1 by dx dn2 by dx and into u2 u3. So from this you can calculate the strain anywhere within the element, and then you can now calculate the stress. So you can calculate sigma xx is equal to E times epsilon xx. So this is how the post processing is done. So you can calculate these quantities. So yeah, I think for today this is where I want to stop. And know if you have any doubts and questions you can ask. And in the next class, I have actually some lecture at the same timing on Thursday, although I'm going to take the lectures on Tuesday, Thursday and Friday, 11 to 12. So next, this coming Thursday I have some lecture for some CP course in one of the institute outside IT. So same timing. So that is why I'm not taking lecture on Thursday. So Friday is a holiday, but I have scheduled the lecture on Friday. So there would be lecture on Friday from 11 to 12, and then the Saturday is also working as per I think Friday timetable. So Saturday also there would be lecture from 11 to 12. So now if you have any questions and doubts, you can ask.
Sir, like suppose we are given any problem, then while solving it, how do we know that which process to apply? Like how, like should we go from a weak form or should we go from the um, delta I method?
Yeah, so if you look at both, he will give you the same element level governing equations. So it is up to you. Whatever, if you have differential equation, you can start with the weak form, or if you can directly write the integral functional, you can start from there. But both will give you the same, essentially the element level governing equations. If no, the for a given weak form, if the integral functional exists, and there could be some differential equation problems where the integral functional does not exist, so there you have to work with the big form only. As I said, no, the odd order, no, if you have differential equation with odd order derivatives, so you may not have the no, the integral functional the way we have written for the couple of problems over here. So there you can start with the big form.
Okay, sir.
But for the problems here, like all the solid mechanics problems, you will have both differential equation and therefore corresponding weak form and integral functional. So if you use the same approximation within the element and same type of element, both will give you the same element level governing equation. So you can start with anyone.
Okay. So, sir, in our course, mostly we will be dealing with the solid mechanics part, right?
Yeah, yeah, we are going to deal with solid mechanics problem. Yes.
Okay.
Yeah. Any other doubt, question, anybody?
Hello, sir.
Yeah.
So if we see the second equation of the global stiffness matrix,
Yeah.
this external force, that is QL, and if we see the first node, second and third node, so at the first node is it QL by 2, second node QL, and third node again QL by 2. So what
Correct.
does it physically signify, sir? Like it is higher at the second node. So
So see, the reason is if you see, the second node gets contribution from both the elements. See,
okay,
if you look at the first node, it has contribution only from the first element. But if you look at the
so
global second node, it has contribution from both element 1 as well as element 2. So that is how it is QL. Third node again has contribution only from the second element, so it is QL by 2. So this QL by 2 plus QL by 2, this term, if you look at it, has that second node. Essentially, if you think of this as a lumped load vector, so the total load along the axial direction is QL, that is equally divided between the two nodes of the element. But the second node gets contribution from first element as well as the second element. So that is how QL by 2 plus QL by 2 comes out as QL.
so means we can say that this part of the beam, sorry, this part of the truss will have the
Yeah,
maximum axial distribution load concentrated at that point.
yeah, right.
Thank you, sir.
Yeah. So anybody else? Any other question? Hello, is there anyone else has any question?
Hello.
Yeah,
Sir, when we take du by dx, we are taking that derivative to that shape function only, and why not to that dE terms?
because the D term is already the values of displacements at two nodes, so they are constant quantities.
But
So
sir, as
u1
they
is
are
the value of
constant,
u at the value of u1 is value of u at node 1, and u2 is value of u at node 2. So they are values at those to a fixed point. The locations were node 1 and node 2. So they are independent of capital X because they are values at a particular points. Whereas if you look at n1 and n2, they are functions of x. So we are differentiating that. For the differentiation purpose, see the u1 u2 are constant quantities but unknown, and n1 and n2 are functions of x. So we are taking the derivatives of that. When we take delta u, the variation of u, so in that, see, n1 and n2 are known quantities, but they are functions of capital X. Whereas u1 and u2, that is elements of D, are unknown quantities. So we take the variation of those. So you rightly said when I write u, so that is n1, n2 into u1 and u2. So when I write du by dx, so see, because these u1, u2 are the values at two nodes, so they are independent of x. u1 is the value at node 1 and u2 is the value at node 2. So when I write du by dx, I am writing dn1 by dx, dn2 by dx, and u1, u2. But when I write variation, so if I want to write delta of u, now the variation is taken with respect to unknown quantities. So unknowns are u1 and u2. So that would be n1, n2, and into delta u1, delta u2. So that is delta DE basically. So this is H into delta DE. Is that clear?
yes, sir. Sir, that means we apply that variation operator only on unknown terms. Am I right?
Yeah, right.
Okay, sir. Thank you.
Yeah. So is there any other question? Anybody? Anybody else? Any question? So if there are no questions, I am stopping here. Thank you all for your attention. Thank you.
Thank you, sir.
Thank you, sir.